This video has the solutions for the second half of the problems from 10-8, numbers 37 to 47 odds. I'll go through them a little faster than we did the first half, because you have us in practice now. Alright, so first problem, we have the series from k to infinity, 3 to the k over k factorial times x to the k. I'm going to go ahead and write out the first three terms. Plugging in 0, I get 1 over 1 times x to the 0. It's not alternating. Plugging in 1, I get 3 over 1 times x to the 1. Plugging in 2, 3 squared over 2 factorial times x squared. And then maybe I'll write out one more. 3 cubed over 3 factorial times x cubed, and so on. Do the ratio test. See where this converges. You might just think about your experience so far and what you think this might do. If you have any intuition yet about that. So, the limit as k approaches infinity of 3 to the k plus 1 over k plus 1 factorial times 3 to the k on the bottom, k factorial on the top. Oops, I forgot the x's. Whoops. X to the k plus 1 and x to the k on the bottom. Canceling out, looks like I got a 3 on the top. Factorials cancel out, leaving a k plus 1 on the bottom, and I forgot to leave room here. So I'll put my x, 1 left over here. That's not affected by the limit. Limit is k approaches infinity, 3, there's only a k on the bottom, highest power's on the bottom, so that's going to infinity. So that means I have to sandwich x times infinity in between -1 and 1, but since I have infinity here, oh sorry, not infinity, I'm just kidding. The highest power is on the bottom, so that's 0. Not infinity. Crazy. And you might have suspected that it would converge everywhere because there's a factorial on the bottom that's really unmatched on the top. So this converges everywhere. Any x value is going to work. So you can say it converges everywhere, you can say it converges from -infinity to infinity, however you want to say that. And I don't have to check endpoints, because there are no endpoints. And the radius of convergence would be just infinity. For 39, I have the sum k equals 0 to infinity of x to the k over 1 plus k squared. Might think about what you know about that kind of series. Maybe thinking about limit comparison. What happens with that series when the x's are not there. Ratio test. Limit as k approaches infinity of x to the k plus 1. Oh, you know what? I forgot to write out my terms. Let me go back and do that real quick. Plugging in 0, I get 1. It's not alternating. Plugging in 1, I get x over 1 plus 1. Plugging in 2, I get x squared over 5 plus x cubed over just one number greater than the perfect squares, right? Alright, so back to this. 1 plus k plus 1 squared times x to the k on the bottom plus k squared on the top. I have one extra x. I didn't leave room there again. Whoops. I'll have to put it at the back. And then I don't really have any way of canceling anything out here, so you could FOIL this out. But the important thing is to realize that this is a polynomial with k squared as the highest power. This is also a polynomial with k squared as the highest power. It's 1k squared over 1k squared, so that gives me 1 times x. So I need to make sure that 1 times x is in between -1 and 1, so my interval is from -1 to 1. But I need to check the endpoints. This is where your limit comparison knowledge might come in handy. When x is equal to 1, then I just get 1 plus 1/2 plus 1/5. And that might be kind of hard to see. Maybe it would be easier to see if we write it like this. Oops, k equals 0 to infinity of 1 over 1 plus k squared. And then we'd say, by limit comparison, yes, this is going to behave like a p-series with k equals 2. So this converges by limit comparison. And so that's at x equals 1, so I'll have to put an equal sign there. At x equals -1, I get the same series as this, but it alternates. So 1 minus 1/2 plus 1/5. And that converges because it's an alternating series and the terms are going to 0. So that's the interval of convergence and the radius of convergence. Radius is equal to 1. Number 41, I have the sum k equals 1 to infinity, -1 to the k plus 1, it's alternating. I have x plus 1 to the k over k. First few terms here. When I plug in 1, I get a positive term, so it's going to start positive. X plus 1 over 1. And then minus, it's alternating. X plus 1 squared over 2 plus x plus 1 cubed over 3, and so on. The first thing to note here is this is the first one that we've seen where it's not just an x here, it's an x plus 1. So thinking about how we build these series and the recipes for Taylor series, this is a series that has not been created at 0 rather, it's been created at -1. All of the ones that we've seen before up to this point have just been an x to the k power. This one is an x plus 1 to the k power. So the center, the place where this series was created, is at x equals -1. So if I get an interval, I should expect that -1 will be the center of that interval, because that's where this series was created. So if it's going to converge on some interval, I would expect -1 to be at the center of that. Let's see what happens. We do the ratio test. That's the limit. As k approaches infinity, I'm going to ditch the sign flipper for the purposes of the ratio test. So x plus 1 to the k plus 1 over k plus 1 times x plus 1 to the k there. And I'm going to remember this time I have one extra x plus 1. I'll put that on the outside here. And I have k over k plus 1. Highest power top and bottom is 1. Ratio of the coefficients is 1. So that's equal to x plus 1 times 1. So that needs to be sandwiched in between 1 and 1. When I subtract 1 from each side here, I get the interval from -2 to 0. And sure enough, that is an interval that is centered around -1. And the radius will still be 1, right? From -1 to 0, -1 to -2. Radius is 1. I still have to check my endpoints. And I don't know, any intuition here about what's going on? Good to think about it, right? Not just blindly go through these, but think about what's happening. When x is 0, then this will just turn into 1 minus 1 over 2 plus 1 over 3, and that converges. That's the alternating harmonic series. So at 0, it converges. How about when x is -2? When x is -2, then every single one of these is going to be equal to -1, right? So looking back at my original series here, or looking at this, it doesn't actually matter, I guess, wherever you look at it. So here I would have -1, and then here minus -2 plus 1 is -1, but it's squared, so that's positive. But I do have this minus sign here. And then here, -2 plus 1, that's -1 cubed is negative, so that would be -1/3, and so on. So I get the negative harmonic series. And if the positive harmonic series, where all the terms are positive, diverges, then of course this also diverges. It just diverges to -infinity. Right? If all the signs are negative, then we could factor out the negative and put it out in front, and then it would have negative the harmonic series, which diverges. So there's my interval and my radius. Number 43. Got another one here that's not centered at 0. K equals 0 to infinity. 3/4 to the k times k plus 5. Sorry, x plus 5 to the k. Right at the first few terms here. When I plug in 0, that's 1 and that's 1. It's not alternating. Then when I plug in 1, I get 3/4 times x plus 5. And then I get 3/4 squared times x plus 5 squared, and so on. All right? Ratio test. What's the limit as k approaches infinity of 3/4 to the k plus 1 times x plus 5 to the k plus 1. And since this one is really, it doesn't really have a denominator, it's not quite structured like the other one, so I'm just going to divide by the next term. I don't have to do the multiplying by the reciprocal game. I have 1x plus 5 left over. So you can see, where is this series centered at? Centered at -5. Then I have here 3/4. I have an extra 3/4 there. Now there's no k's in here, so the limit as k approaches infinity of 3/4 is just 3/4. There's no k's in there at all. So I have 3/4 times x plus 5. I need that to be sandwiched in between -1 and 1. Well, let's see what we need to do here, a little bit of algebra. So multiply through the whole inequality by 4/3. And then subtract 5 from every wire. And 5 is the same as 15/3. So this would be negative 19/3 less than x less than negative 11/3. And you can see, indeed, the center of that would be negative 15/3 or negative 5. And while we're at it, the radius here, probably easiest to see here, the radius, it goes up 4/3 and down 4/3 from negative 5. So the radius is 4/3. We'll check our endpoints, which are, the endpoints are negative 11/3 So let's see, what do we get when I plug in negative 11/3 and I add 5 to that? Well, that's like going back here one step. When I add 5 or 15/3 to that, I get 4/3. So each one of these parentheses is going to be equal to 4/3. So that would be 1 plus 3/4 times 4/3 is 1 plus 3/4 squared times 4/3 squared is 1, and so on. That diverges. And then we also have to check negative 19/3. Every time I add 5 to negative 19/3, I get negative 4/3. So it gives me 1, and then here I'm doing the exact same thing, but all my odd terms, this is negative 4/3 squared, so the negative doesn't matter, so that's plus 1, and so on. And that diverges. If you're tempted to say that this converges to 0, it doesn't. Remember that the very first thing that has to be true for a series to converge is the terms have to be getting closer and closer to 0, and these are not. So this does not converge. So that diverges. Both endpoints failed. So there's our answer there. Two more. Number 45. I have the sum from k equals 1 to infinity. Negative 1 to the k is alternating. It's x plus 1 to the 2k plus 1 over k squared plus 4. Let's write out the first few terms here. First term is going to be negative. When I plug 1 in here, I get x plus 1 cubed over 5 plus x plus 1. When I plug 2 in here, I get 5. This is how you make an odd number, right? 2k plus 1. And then on the bottom, I have 2 squared plus 4. And then I'm going to have a negative term, next odd number, and then 3 squared is 9 plus 4. So perfect squares plus 4, right? 1 plus 4, 4 plus 4, 9 plus 4, 16 plus 4 would be the next one, and so on. Okay, do the ratio test. So what's the limit? As k approaches infinity. I don't care about the sign flipper for the ratio test, so I'll leave that off. I have x plus 1 to the, when I plug k plus 1 in here, the 2 distributes through that. It gives me 2k plus 2 plus 1. That's 2k plus 3. Right, that makes sense. When you tick up the k by 1, you get the next odd number. 2k plus 3 is the next one up from 2k plus 1. And on the bottom I have k plus 1 squared plus 4 times x plus 1 to the 2k plus 1, k squared plus 4 on the top. Now this is bigger than this exponent by 2. So that means I have x plus 1 squared outside here. And the limit as k approaches infinity of something with the highest power of k squared and a coefficient of 1 in the bottom. If I FOILed that out, I would have something with a k squared with a coefficient of 1. So that's just equal to x plus 1 squared times that limit's 1. Okay, so I need to take x plus 1 squared and sandwich that in between negative 1 and 1. Now, this is a little bit tricky, I think. Got to think about what's happening here. Now, of course, when x plus 1 gets squared, it's not going to be negative, right? And saying that x plus 1 squared is in between negative 1 and 1, well, what kind of numbers, like what does it mean to square something and have it between negative 1 and 1? It's always going to be positive, so it would be true that really what I'm interested in this is this. And I don't know if you know, thinking back to Algebra 2 or just using a little bit of logic here, if when I square root this, it does give me this, right? I just take the square root of this and the square root of that. But what about negative numbers? There are negative numbers that you could square, right, and still get something less than 1. So these are the negative numbers that you could square and still get something less than 1. For example, if I plugged in negative 1/2, I'd still get 1/2 here squared. That works. Negative 9/10, that works. 0 works. So we're good inside this interval here. Right? Okay. We're convinced of that. We will see that the odd time. So that means subtracting 1 here, I get an interval that looks like that. And that makes sense. That's an interval that's centered at negative 1. This is a series that's centered at negative 1, right? All those x plus 1s. So that's consistent with what we would expect. Now we have to check the endpoints. X equals 0. So every time I plug in 0 for x, I just get a 1 here. So that means everything just turns into 1s. The signs remain the same. So I get negative 1 over 5 plus 1 over 7 minus 1 over 9. Oops, sorry, where am I getting those numbers? 8, sorry, 13. And so by the alternating series test, it's alternating and the terms are getting smaller to 0. So that converges. And that converges there. Then I check x equals negative 2. When I plug negative 2 in, then every one of these is going to turn into a negative 1. Negative 2 plus 1 is negative 1. So when I cube negative 1, I get a negative, which makes this positive 1/5. When I cube negative 1 here, when I raise it to the 5th power, rather, that makes negative, so that's going to be negative. And when I raise negative 1 to the 7th power, it's going to be negative. Hitting that, it's going to be positive. So I get just the opposite alternating series, but it's still alternating and the terms are still going to 0. So it does still converge there. And the radius of convergence is 1. Sorry, just making sure I put the radii on all of those. Number 47, last one. The sum k equals 0 to infinity of pi to the k times x minus 1 to the 2k over 2k plus 1 factorial. There's a factorial on the bottom. And thinking about our experience here, when you have a factorial on the bottom, you get a pretty good chance that this is going to converge everywhere. And that would be nice, because then we don't have to check endpoints. Nice way to go out. So let's see. Oh, let me write out my terms first. Plugging in 0, that's 1, 1, and 1. It's not alternating. Plugging in 1, I get pi times x minus 1 squared. Over plugging in 1 here, I get 3 factorial. Plugging in 2, I get pi squared times x minus 1 to the 4th over 2 plus 1, 5 factorial. So a little harder to see the pattern here, maybe. The powers of pi keep going up by 1. The powers on the x minus 1 are even numbers, and these are 2k plus 1, so 1 bigger than what the exponent was for the factorials. Okay, in the ratio test. And we think, based on our experience, this is going to converge everywhere. Let's see if we can demonstrate that. When you plug in x plus 1 here, the 2 distributes through it, and you get 2x plus 2. Likewise, you get 2k plus 2 here, plus 1 is 2k plus 3 factorial. And we get the original upside down. Alright, so what do we have for x's here? I have, well, the pi's also are not inside the, oh no, they do have k's, so I guess I do, oh no, but once we cancel them, I got pi to the k plus 1 and pi to the k, so there's 1 pi left over. I can bring that outside my limit because it's just a constant. And then here I've got 2 extra x minus 1's. And then the inside of the limit, when we cancel out these factorials, this is 2k plus 3 times 2k plus 2, and then 2k plus 1 all gets wiped out by this. So I have nothing left on the top. I have 2k plus 3 times 2k plus 2 on the bottom. And that's equal to pi times x minus 1 squared times only k's on the bottom, k squared on the bottom, no k's on the top, so that's going to approach 0. And then you can write it out if you want. Got a sandwich of this in between -1 and 1, because we want it to behave like a geometric series, right? That's why we do this. And of course any x value at all is going to work because we're multiplying by 0. So that means this does indeed converge everywhere. It converges everywhere. Factorial.